Have you ever wondered why everything in the universe is spinning and yet we feel completely, utterly still? It is a paradox that sits at the very heart of our existence, a quiet contradiction humming just beneath the surface of our reality. The Earth, this beautiful, fragile sphere we call home, is turning at this very moment at over 1,000 miles per hour, a dizzying speed that we have learned to ignore. At the same time, this planetary vessel is orbiting our Sun, a star 93 million miles away, at a blistering pace of 67,000 miles per hour. And as if that were not enough, the entire solar system itself, our Sun and all its children, is racing through the vast, spiraling arms of the Milky Way galaxy at nearly 500,000 miles per hour. And still, you do not feel a thing. Your heartbeat does not tremble. Your breath does not sway as if caught in a cosmic gale. We feel as though we are frozen inside a universe in perpetual, frantic motion. But what if that stillness is the greatest illusion of all? What if the quiet calm you feel right now is not the absence of movement, but the perfection of it? What if time itself, the very ticking of the moments that make up your life, is just the echo of a deeper, more ancient rotation? A rotation that began before atoms, before light, before memory itself was even a concept. Tonight, here on Whispers of the Universe, we will drift into that profound mystery. We will ask not just why things move, but why nothing, absolutely nothing, can ever truly stop moving. So find a quiet place, close your eyes, if you feel comfortable. Let the sound of the cosmos hum beneath your skin, a silent vibration that has traveled for eons to find you. And follow me into the spinning heart of everything. Before we begin our journey into the cosmic whirlwind, if you feel so inclined, a gentle like on this video or a quiet tap on the subscribe button would mean the world to me. It is such a small gesture in the grand first scheme of the cosmos, but I hold it with the deepest gratitude. Every bit of your support keeps this tiny universe alive and reminds me that these quiet stories, these whispers of wonder, still find their way to gentle hearts like yours. Now, let the journey commence. Have you ever stood on a quiet night, far from the glare of city lights, and looked up at the stars? They appear as fixed points of light, eternal and unmoving, a silent celestial tapestry. It is an image of profound stillness, a portrait of cosmic peace. But that peace is a magnificent deception. The reality is that you are standing on the surface of a colossal gyroscope, a planet spinning with a velocity that would tear apart any man-made machine. The ground beneath your feet is moving at a speed faster than sound, yet the coffee in your cup does not ripple. The air around you does not drag against your skin like a hurricane. The stars, which are themselves hurtling through space at unimaginable speeds, appear perfectly still. This is one of the great illusions of existence, a beautiful and bewildering paradox of furious motion and absolute calm. Why, if every single thing from the smallest electron to the largest supercluster of galaxies is in a state of constant rotation, do we feel so profoundly, so convincingly frozen in time? The answer, like so many secrets of the universe, begins with a concept so fundamental, so quiet, yet so powerful that it governs every moment of our lives. It is a principle known as inertia, first described with elegant clarity by Sir Isaac Newton in the 17th century. The law of inertia is deceptively simple. An object in motion stays in motion unless acted upon by an external force. This single, elegant law is the secret reason we do not feel the Earth's endless, silent spinning. We are not moving times on times the Earth. We are moving times with times the Earth. Your body, the chair you are sitting in, the air filling your lungs, the vast oceans, the towering mountains, every single particle of this planet is turning together, locked in a single, silent, harmonious rhythm. To feel motion, your senses require a change, a difference, a push, a pull, an acceleration, or a deceleration. But here, on this gracefully spinning planet, there is no such change. The Earth's spin is remarkably constant, impossibly smooth, and unimaginably ancient. The rate of its turn is the same now as it was when the first early humans looked up at the same unmoving stars and felt the same profound stillness. Feel your own breath for a moment. Is it rushed? Does your heart race with the speed of a planet hurtling through the void? No, it is calm. And in that calm, have you ever felt disconnected? As if you are merely an observer on a grand stage, while the real drama of the universe unfolds at speeds and scales you can never truly touch? What if that feeling of separation, that sense of being a still point in a turning world, is not a limitation, but a key? What if it is the very thing that allows us to perceive reality at all? This illusion of stillness is not unique to us. Astronauts, our brave voyagers into the celestial ocean, experience this same paradox on an even grander scale. In low Earth orbit, they travel at the mind-boggling speed of 17,500 miles per hour, circling our entire planet every 90 minutes. They witness 16 sunrises and 16 sunsets in a single Earth day. Yet, inside their spacecraft, everything feels calm. A pen floats motionless in the air. A drop of water hangs suspended, a perfect, shimmering sphere. Without the resistance of an atmosphere, without the friction of air, motion feels exactly like stillness. This phenomenon has a name in physics: uniform motion. It is the very same principle that allows you to walk down the aisle of an airplane traveling at 500 miles per hour and feel as if you are standing still. You, the plane, the air inside, and the cup of tea on your tray table are all moving together as a single, unified system. It is only when turbulence hits a sudden change, an external force that interrupts that uniformity, that you are violently reminded of the incredible speed at which you are traveling. The Earth's motion, by comparison, is almost perfectly seamless. There is no celestial turbulence. There are no cosmic vibrations, no friction against the vacuum of space, no sudden shifts in velocity to jolt our senses. And because space is almost a perfect vacuum, an emptiness more profound than anything we can create on Earth, there is nothing to push against us, nothing to remind us that we are spinning at cosmic speeds. The astrophysicist Neil deGrasse Tyson once so beautifully articulated this perspective when he said, "We are on a space rock that is orbiting a star, that is orbiting a galaxy that is moving through the universe, and we call it home." It is so easy to forget this cosmic context because our senses, our entire biological systems, were never built for such scales. Our inner ears, the delicate, fluid-filled labyrinths that detect motion and maintain our balance, evolved to handle the modest accelerations of walking, running, or climbing a tree. They were not designed to perceive the steady, constant rotation of a planet thousands of miles wide. They are exquisitely sensitive to acceleration, not to steady velocity. That is precisely why you feel the lurch of a car as it starts, but you do not feel its motion as it cruises smoothly down the highway. On Earth, everything moves with you. There is no start or stop to our planet's journey, only an eternal, silent glide through the cosmos. And yet, even though our senses are blind to this motion, the brilliant minds of scientists have devised ways to measure this hidden movement with remarkable precision. One of the most elegant proofs is the Foucault pendulum, first demonstrated in the year 1851 by the French physicist Léon Foucault. Imagine a heavy, massive pendulum suspended from a great height, allowed to swing freely back and forth. Its path of oscillation appears to slowly, almost magically, rotate over the course of a day. But it is not the pendulum that is turning. The pendulum, governed by the law of inertia, maintains its original plane of swing with unwavering fidelity. It is the floor, the city, the continent, the entire planet that is slowly and silently turning beneath it. The Foucault pendulum does not need to see the stars to prove the Earth's rotation. Its slow, graceful twist over hours is the planet's spin made visible, a silent, mechanical dance that visualizes the merging of time and motion, one gentle swing at a time. If you have ever had the chance to stand near one of these magnificent devices in a science museum, perhaps at the Griffith Observatory in Los Angeles or the Smithsonian in Washington, D.C., you have witnessed a profound truth. You have seen the Earth's secret, movement revealed in the most tranquil way imaginable. On a cosmic scale, this rotation is far from trivial. It is the engine of our world. The Earth's spin defines the fundamental rhythm of our lives, day and night. This constant turning also stabilizes our planet's powerful magnetic field, an invisible shield that protects all life from the harsh onslaught of solar radiation. Without this spin, our world would be a desolate, uninhabitable rock, scorched on one side and frozen solid on the other. The National Aeronautics and Space Administration's Goddard Space Flight Center notes that our planet's rotation has been gradually slowing down over billions of years, a process driven primarily by the gravitational pull of the Moon. This tidal interaction adds about 1.7 milliseconds to the length of each day, every century. So even in our perceived stillness, there is change that is slow, invisible, and yet absolutely real. The very length of our day is not a constant, but a slowly evolving measure of our planet's cosmic story. When we look deeper, we find that rotation is not just an earthly phenomenon. It is a cosmic signature, a fundamental characteristic written into the very fabric of the universe. Stars, for instance, are born from the collapse of vast, swirling clouds of gas and dust. As these clouds shrink under their own gravity, they spin faster and faster. This is due to a law known as the conservation of angular momentum, the same physical principle that makes a figure skater spin faster when she pulls in her arms. Every planet in our solar system inherited this primordial momentum from the nebula that birthed it. The Earth's 24-hour rotation is a fossilized trace of that ancient whirlpool of creation, a memory of our cosmic origins. Even our sun spins, completing one rotation approximately every 27 days, dragging its immense magnetic field through space like glowing, ethereal threads. And our home galaxy, the Milky Way, is itself a colossal spinning vortex. It turns once every 230 million years, a grand, majestic rotation carrying hundreds of billions of stars in a spiral dance that began long before our planet ever existed. The James Webb Space Telescope, our newest and most powerful eye on the cosmos, has captured images of galaxies so far away that their light has been traveling for over 13 billion years to reach us. And even in these primordial galaxies, these first whispers of cosmic structure, scientists see the telltale signs of rotation. Researchers from the European Space Agency, studying these ancient formations, have found subtle differences in the light they emit. One side of a distant galaxy might be slightly red-shifted, meaning it is moving away from us, while the other side is slightly blue-shifted, moving towards us. This is the unmistakable signature of spin. It seems that the tendency to rotate, to turn, to move in a grand, circular dance is written into the universe's very DNA. But how can everything, on every scale, be spinning, and yet we feel so incredibly still? Part of the answer lies in one of the most profound ideas in all of science: relativity. According to Albert Einstein, there is no such thing as absolute motion. There is only motion relative to something else. From our perspective here on Earth, we are at rest, and it is the entire universe that moves around us. The sun rises and sets, the stars wheel across the sky. From another frame of reference, perhaps that of an observer on a distant planet, the opposite is true. This fundamental symmetry is what keeps the laws of physics consistent throughout the cosmos. And it is what makes our stillness and beautiful illusion of perspective. In the silent, weightless environment of deep space, astronauts aboard the International Space Station orbit the Earth at nearly 5 miles per second. Yet they do not experience a sensation of motion. They experience weightlessness. Their sense of down changes every 90 minutes as they circle the globe. Yet their minds adapt, recalibrating to the new reality. We, too, are passengers in constant motion, perfectly adapted to the calm of our cosmic vessel. Our stillness is a form of survival, a delicate and precise balance between what our senses can bear and what the cosmos demands. If we could somehow feel the raw motion of the Earth, the relentless gravitational pull of the Sun, the majestic drift of our galaxy, our perception of reality, and perhaps even of time itself, would unravel. Because motion and time are not separate things, they are inextricably intertwined. As rotation defines our days and our years, it also defines the very heartbeat of the cosmos. Time, as the great astronomer Carl Sagan once said, is woven into the very fabric of the universe, and we, each of us, are a thread in that magnificent tapestry. The quiet you feel now is not the absence of motion, it is the perfect harmony of everything moving together, as one. So when you lie down tonight, beneath the invisible turning of the stars, remember this profound truth. You are not standing still. You are gliding through a cosmic river, gently, constantly, endlessly. Each moment of your perceived stillness is just the universe moving too smoothly, too perfectly, for you to notice. And in that perfect balance of motion and calm, life finds its quiet, unwavering rhythm. Take a slow, deep breath. You are spinning. You always have been, and the silence you hear is the sound of everything moving together. Now, as we drift deeper into this cosmic story, let us look backward, not just through history, but through time itself. Let us journey to the moment before motion as we know it began, to the instant when the universe itself took its very first turn. If you could somehow turn back the clock, not by centuries, not by millennia, but all the way to the very first infinitesimal second after the Big Bang, what would you see? Would there be light? Would there be sound? Or would there only be a sudden, primordial motion, a swirl, a twist, the very first rotation of everything that would ever exist? The question of who, or what, gave the universe its first spin is not merely a question of philosophy, but one of fundamental physics. It lies buried deep within the complex equations of cosmology, hidden inside the earliest moments of time, when matter, energy, and space itself first began to unfold. Astronomers call this impossibly brief period the Planck era, a window of time so early within 10 to the power of negative 43 seconds of the Big Bang that our current laws of physics cannot fully describe it. It is a realm where gravity and quantum mechanics merge, where our understanding of reality breaks down. But what little we can infer from our theories suggests something extraordinary. Silence and stillness, but in a gentle, all-encompassing rotation. Today, scientists studying the cosmic microwave background, or CMB, the faint, ancient afterglow of the Big Bang detected by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite from the European Space Agency, have found tiny, almost imperceptible irregularities. These are minuscule ripples in temperature, differences of only a few millionths of a degree from one part of the sky to another. These patterns are of monumental importance. They tell us that the early universe was not perfectly uniform. There were slight differences in density and energy, and it was these differences that, over billions of years, grew into everything we see today: galaxies, stars, planets, and life itself. But within this data, some researchers noticed something even stranger, something that did not quite fit the standard model. They found a faint alignment, a kind of large-scale, mysterious twist in the forced distribution of those temperature ripples. They controversially nicknamed it the axis of evil. Not because it was sinister, but because it was a perplexing, unwelcome pattern that challenged our most fundamental assumptions about the cosmos. This mysterious alignment, first hinted at in data from the National Aeronautics and Space Administration's WMAP mission, and later seen with more clarity by the European Space Agency's Planck satellite, could mean one of two things. It could either be a subtle artifact of our measurement techniques, a cosmic fluke, or it could be hard evidence that the entire universe, on the largest of scales, once had a preferred direction of rotation. If this is true, that primordial spin might have shaped everything, from the graceful spiral arms of galaxies to the very arrow of time itself. But how could such a universe-spanning rotation even begin? The key might lie in the strange and wonderful world of quantum fluctuations. These are tiny, random, and spontaneous changes in energy that occurred when the universe was smaller than a single atom. Even in what we would consider complete emptiness, a perfect vacuum, these quantum fluctuations happen naturally. As the National Aeronautics and Space Administration's Goddard Space Flight Center describes, quantum fields are never perfectly still. They jitter. They seethe with a constant underlying energy. When the Big Bang happened, these microscopic jitters were stretched and amplified by a process called cosmic inflation, a brief but unbelievably explosive period of expansion that made the universe grow faster than the speed of light. That rapid, violent stretching could have taken some of those random quantum jitters and transformed them into coherent, swirling motions, the very first cosmic spins. The theory of inflation, first proposed by the physicist Alan Guth in 1981, brilliantly explains why the universe appears so smooth and uniform on large scales, yet still contains the tiny seeds of structure that grew into galaxies. But in recent years, data from experiments like Planck and Bicep 2 have suggested that during inflation, subtle rotational modes, known as B-modes, may have existed in the primordial gravitational waves. These tiny curls in the fabric of space-time itself could be the fossil record of the universe's first rotation. They would show that the Big Bang was not just a simple outward explosion, but a twisting, turning birth. A birth that imprinted the property of spin across every scale of matter for all of time. And this makes perfect sense when we look at what happened next. As the universe expanded and cooled, matter began to form first quarks and gluons, then protons and neutrons, and finally, the first atoms of hydrogen and helium. Each of these particles carried with it a tiny, intrinsic amount of angular momentum. When gravity later began to gather these particles into vast clouds, and then into the first proto-galaxies, that ancient, primordial, angular momentum was conserved. It is the very same principle that makes a spinning figure skater accelerate when she pulls in her arms. In physics, nothing can spin from nothing. Motion must come from pre-existing motion. And so the first spin, however small, however subtle, had to exist from the very beginning. Today, astronomers can see the fingerprints of that primordial rotation in distant galaxies. In the year 2011, a team of researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies and found a subtle, yet statistically significant, preference in their direction of rotation. It was an imbalance, a handedness to the cosmos that might trace all the way back to the early universe's spin. While the evidence is not yet conclusive, this cosmic handedness hints that our universe may not be entirely random after all. There may be a hidden rhythm, a silent, universal turn, that everything still follows. Even dark matter, that mysterious, invisible scaffolding that holds galaxies together, could carry a signature of this ancient spin. Sophisticated computer simulations run at the National Aeronautics and Space Administration's Jet Propulsion Laboratory show that dark matter halos, the vast, invisible spheres in which galaxies are embedded, twist and rotate over billions of years. They guide the visible galaxies within them, like immense, slow-moving whirlpools guiding leaves on the surface of a pond. Without that gentle, organizing rotation, galaxies would likely tear themselves apart under their own gravitational forces. It is as if the early universe set everything spinning, and even now, 14 billion years later, the echoes of that first motion are what keep the stars in their delicate balance. Still, the ultimate origin question remains: who or what began the spin? Physicists, when pressed for an answer, lean on one quiet and profound concept: symmetry breaking. In the earliest, hottest fractions of a second, the forces we now know as gravity, electromagnetism, and the strong and weak nuclear forces were all believed to be unified into a single, perfect force. But as the universe cooled, they began to split apart, one by one. When that perfect symmetry broke, tiny asymmetries, tiny imperfections, appeared in the fabric of reality. Those imperfections, according to the European Space Agency, are what allowed structure, motion, and spin to exist in the first place. In a perfectly balanced, perfectly symmetrical universe, nothing could ever move. But in a slightly unbalanced one, it could dance. We can see this principle of broken symmetry mirrored everywhere in nature, from the preferred direction in which some galaxies spin, to the way certain atoms rotate, and even in the bizarre fact that all neutrinos seem to have a left-handed preference. Nature, it seems, is not perfectly symmetrical, and that tiny, fundamental flaw is what allows everything to turn. Some scientists have even tried to detect whether the entire universe is still rotating on the largest of scales. In 2020, astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. He found compelling evidence that galaxies in one half of the sky tend to rotate more in one direction than the other, suggesting a vast, large-scale cosmic spin. As Shamir wrote in his paper, the universe may have a collective pattern of motion, a preferred direction that began in the chaos of the early universe. This does not mean the cosmos is spinning like a top in some higher dimensional space. Rather, it might mean that the fabric of space-time itself once twisted slightly during its initial expansion. Even a subtle twist at the beginning could cascade across billions of light-years, shaping the geometry of everything we see. To us, it feels completely invisible. But on a universal scale, it could be the silent architect of the cosmos. To test these extraordinary theories, the National Aeronautics and Space Administration and the European Space Agency continue to map the universe in ever-increasing detail. The James Webb Space Telescope is already capturing the light of galaxies that formed just 300 million years after the Big Bang. Some of these incredibly ancient systems already show signs of organized rotation, with spiral patterns forming far too early in cosmic history to be explained by chance encounters alone. That implies that the seeds of spin were planted almost immediately. The universe did not have to learn how to rotate. It was born turning. Even on the most fundamental level imaginable, the quantum level, spin is an intrinsic property of reality. Every particle, electrons, protons, neutrons, carries what is known as intrinsic spin, a built-in property of matter described by the laws of quantum mechanics. It is not the kind of spinning we imagine in our everyday world, like a spinning ball. It is a deeper, more abstract mathematical rotation encoded in the wave function of the particle itself. As the great physicist Richard Feynman once said, spin is one of the most profound properties of nature. It is not that the particle is literally spinning, it simply has spin, just as it has mass. So, in a way, rotation was not added to the universe later. It was part of the original blueprint of existence. When you look up at the night sky, you are seeing the direct inheritance of that first motion. Every galaxy's swirl, every planet's orbit, every single photon of light that strikes your eye, all descend from that first, primordial cosmic rotation. Without it, matter would never have clumped together, stars would never have formed, and time itself would have no rhythm, no measure. Motion is not an accident of the universe. It is its heartbeat. And though we may never know with absolute certainty what triggered that first spin, the evidence keeps whispering the same story. It has always been there. Quiet, steady, invisible, yet written into everything we can see and touch. As the European Space Agency cosmologist Jan Tauber once said, the universe carries memory, not in words, but in patterns of light. And within those patterns lies the faint signature of the first motion, a twist older than time itself. So when we ask who set the universe spinning, The most honest and beautiful answer may be that the universe never learned to move. It was born already in motion. The spin was not created. It was inherited. Take a deep breath. The atoms in your body, too, are still turning with that first, ancient impulse. From the tiniest electron to the vast swirl of the Milky Way, the same rotation continues, unbroken for nearly 13.8 billion years. We are not separate from that motion. We are its continuation. And as we move onward through this story, we arrive at the next logical question, one that flows naturally from the last. If rotation shaped the birth of the universe, could it also be the fundamental reason that life itself exists? That is where we turn next. Without rotation, our Earth would be a silent, dead world. There would be no day and no night. There would be no weather, no wind, no seasons. There would only be a frozen side, locked in eternal darkness, and a scorched side, baked under a relentless, unmoving sun. It would be a planet of violent extremes, a dead world adrift in a sea of light. But because it spins, this planet breathes. Every sunrise, every ocean wave, every gust of wind, they all come from the same ancient turn that began 4.5 billion years ago, when our world first coalesced from a swirling disk of dust and gas. The Earth's spin is not just a motion. It is an engine, a delicate, life-sustaining balance that underpins everything we know as life. From the powerful magnetic field that shields us from deadly cosmic radiation to the global cycles of temperature that nurture our oceans and clouds. Rotation shapes our world in ways both visible and profoundly invisible. According to the National Aeronautics and Space Administration's Goddard Space Flight Center, our planet's rotational speed at the equator is about 1,037 miles per hour. It completes one full spin every 23 hours, 56 minutes, and 4 seconds, what scientists call a sidereal day. This steady, predictable rhythm sets the pace for all biological and environmental cycles on Earth. Every plant, every animal, and every ocean current is synchronized to this invisible cosmic metronome, ticking steadily beneath everything that is alive. The first and most obvious consequence of Earth's rotation is the beautiful and constant alternation of day and night. This regular cycle distributes the sun's energy across the planet's surface, creating the temperature gradients that drive wind, currents, and all of our weather systems. Without that daily rotation, one hemisphere would roast under perpetual daylight, with temperatures soaring high enough to boil water, while the other would freeze in eternal darkness, a wasteland of ice and silence. The boundary between them, a narrow twilight zone, would be a region of unimaginable violence, a permanent wall of storms whipped up by the extreme temperature differences. But because our Earth spins, the sun rises and sets, and that life-giving energy is shared evenly enough to allow for stable climates and vast habitable regions to flourish. Rotation also has a profound effect on Earth's magnetic field, one of the most crucial shields for life. Deep beneath our feet, the planet's liquid iron outer core moves and churns, a roiling ocean of molten metal. This motion, driven by the planet's spin and convection currents, generates a powerful magnetic dynamo. As the National Aeronautics and Space Administration's magnetospheric multi-scale mission describes it, the Earth's magnetic field is created by the complex motion of molten iron within its core. This invisible field extends thousands of miles out into space, deflecting the solar wind, a constant stream of charged particles emitted by the sunday. Without this protective magnetic shield, those particles would bombard our upper atmosphere, slowly but surely stripping it away, just as it did on ancient Mars. The red planet spins once every 24.6 hours, a day length remarkably similar to Earth's, but its smaller core cooled and solidified long ago, causing its magnetic dynamo to cease. Without a working magnetic field, Mars's once thicker atmosphere was slowly eroded by the sun's relentless radiation, leaving behind the dry, cold, frozen desert we see today. Here on Earth, our magnetic field also shapes the auroras, those soft, glowing curtains of light that dance near the poles. They are not just a beautiful spectacle, they are proof of our planet's protection. Where the magnetic field lines bend down and interact with charged solar particles, light is born, a shimmering reminder that our planet's rotation still powers an invisible force field around us. But the spin's influence does not stop at shielding and sunlight. It also governs the very circulation of our atmosphere. Because the Earth turns, air moving from the equator toward the poles is deflected, curving into vast, swirling patterns. This phenomenon is known as the Coriolis effect. This effect is responsible for creating the vast, spiraling systems of winds and ocean currents that define our planet's climate. It is the reason why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern. It is why the jet streams, those high-altitude rivers of air, flow in predictable paths across the globe. And it is why great ocean gyres carry warm and cold water between the equator and the poles, regulating global temperatures. Without the Coriolis effect, weather patterns as we know them would collapse into chaos. Organized storms would not form, and our climates would not be able to balance themselves. In fact, the precise rotation speed of a planet directly shapes its climate. The National Aeronautics and Space Administration's Global Modeling and Assimilation Office has run sophisticated computer simulations of exoplanets with different, slower, or faster spin rates. A slower rotation causes one side of a planet to overheat and the other to freeze, creating extreme temperature gradients. A faster rotation, on the other hand, can generate extreme winds and shorter days that disrupt atmospheric stability and prevent life from gaining a foothold. Earth's 24-hour rhythm appears to be almost perfect for life, long enough to distribute energy evenly across the surface, but short enough to prevent any one region from overheating or overcooling. The length of our day also has a profound effect on biology itself. Over billions of years, living organisms have evolved internal clocks, known as circadian rhythms, that are precisely aligned with our planet's rotation. According to research published by the National Center for Biotechnology Information, every living cell on Earth, from the simplest bacterium to the most complex neuron in your brain, carries a molecular timekeeper that is synchronized to this 24-hour cycle. This internal rhythm regulates when plants open their leaves to the sun, when birds begin their long migrations, and even when we humans feel sleepy or alert. If the Earth were to suddenly stop rotating, this deep biological harmony would shatter. The regular cycle of light and dark would vanish, and life, as we know it, could not adapt. Rotation also played a crucial role in how the Moon became our constant celestial companion. Billions of years ago, a Mars-sized object, which scientists have named Theia, collided with the young, molten Earth. The cataclysmic impact sent a vast amount of debris into orbit, which later coalesced under gravity to form the Moon. The collision also significantly increased Earth's spin, dramatically shortening its day. Over the eons, the Moon's gravity has been acting as a brake on our planet, gradually slowing that rapid spin and lengthening our days from about 6 hours in the distant past to the 24-hour cycle we have now. At the same time, these tidal forces between the Earth and Moon keep our planet's axial tilt remarkably stable, preventing the extreme climate swings that would result from a wobbling axis. The European Space Agency's Gaia mission has confirmed that this axial stability is essential for long-term habitability. Planets that wobble too much often experience catastrophic climate variations that would make the evolution of complex life impossible. The Moon and Earth now exist in a slow, graceful gravitational embrace. The same tides that shape our oceans also continue to slow our planet's rotation by about 1.7 milliseconds per century, a fact recorded with incredible precision by the National Aeronautics and Space Administration's Jet Propulsion Laboratory. It is a constant reminder that even the length of our day, the fundamental heartbeat of our world, is gradually changing, one imperceptible moment at a time. If we look beyond our own planet, we find that rotation plays a similarly critical role in shaping other worlds. Jupiter, for example, spins once every 9 hours and 56 minutes, making it the fastest rotating planet in our solar system. Its incredible speed drives ferocious jet streams and colossal storms, including the Great Red Spot, a hurricane larger than the entire Earth that has raged for centuries. Rotation on Jupiter creates chaos, yet it also creates a form of stability, distributing heat from its interior and shaping the planet's beautiful, banded appearance. Meanwhile, Venus, which rotates backward and extremely slowly, one full rotation every 243 Earth days, has almost no magnetic field. Its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system, with surface temperatures high enough to melt lead. The comparison is striking. Too fast, and violent storms dominate. Too slow, and protection disappears. Even Mars, with a day just 40 minutes longer than ours, shows what happens when a planet's internal motion fades. As its core cooled and solidified, its once strong magnetic field vanished, allowing solar radiation to strip away most of its air and water. The faint remnants of that ancient magnetism still linger in the Martian crust, ghostly traces of a spin that once sustained a dynamic and perhaps even living world. Rotation, then, is not optional for habitability. It is fundamental. In 2023, scientists using the James Webb Space Telescope observed the atmospheres of exoplanets like WASP-39b and TRAPPIST-1e. They discovered that those with a measurable spin or atmospheric circulation show clearer signs of chemical balance and temperature distribution. Without rotation, energy on a planet remains trapped or is quickly lost, creating unstable and inhospitable environments. As the National Aeronautics and Space Administration's Exoplanet Exploration Program summarizes, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation may also be directly tied to the presence of magnetic protection on distant worlds. A study from 2021 by the Harvard-Smithsonian Center for Astrophysics noted that exoplanets with rapid spins tend to maintain molten metallic cores for longer periods, extending the life of their protective magnetic fields. Those fields, in turn, shield atmospheres from stellar winds and may significantly increase the likelihood of surface liquid, water, the essential ingredient for life as we know it. So, when we ask, did spinning make life possible? The overwhelming body of scientific data says yes. Rotation shapes everything from a planet's day length to its temperature gradients, its atmosphere, its weather, and its magnetic safety. Life, it seems, thrives, not despite motion, but because of it. Our world's rotation speed has changed over the eons, yet its effects continue to echo across time. It controls the rhythm of the tides, the growth of forests, the migrations of animals. It defines our very sense of time itself, not as an abstract idea, but as the physical, tangible turning of the world beneath our feet. As the astrophysicist Neil deGrasse Tyson once so eloquently said, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Take a moment to feel that turn. Every rotation of our planet carries the whisper of 4.5 billion years of delicate balance and constant motion. If the Earth stopped spinning tomorrow, the oceans would surge toward the poles in a global tsunami. The atmosphere would collapse into chaos, and our planet would lose its breath. But tonight, as it spins gently beneath you, everything still works perfectly, quietly, continuously. So perhaps it is no exaggeration to say that the rotation of the Earth is the quiet, unsung architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into you. Now, as we drift deeper into this cosmic journey, let us follow that rotation outward, to the extreme edges of reality, to where spinning no longer just shapes life, but begins to bend something even stranger, even more fundamental. Because beyond a certain speed, beyond a certain density, rotation does not just move matter. it can start to twist time itself, and that is where our next chapter begins. When rotation reaches its absolute limit, it stops being simple motion and becomes a form of profound distortion. At extreme speeds and in the presence of immense gravity, turning objects no longer just move through space, they begin to pull and drag at the very fabric of time itself. Albert Einstein's general theory of relativity, published in the year 1915, predicted this strange and beautiful effect. His theory showed that gravity and motion are inseparable, two expressions of the same fundamental reality: how mass and energy curve the four-dimensional fabric of space-time. The greater the mass, the greater the energy, or the faster the spin of an object, the more it twists the geometry of reality around it. This twisting of space-time by a rotating object is called frame dragging, and it is one of the most subtle, beautiful, and now experimentally verified predictions of modern physics. Imagine space-time as the surface of a calm, deep lake. When a massive object like the Earth or a black hole spins, it stirs that lake, creating tiny, invisible vortices in the very flow of time. In those cosmic whirlpools, the direction of time itself, what we perceive as the future, can begin to curve. The National Aeronautics and Space Administration physicist Francis Everett, who led the landmark Gravity Probe B experiment, once described it like this: as the Earth rotates, it drags space-time around with it, much like a spinning sphere would twist the honey in which it is immersed. The Gravity Probe B satellite, launched in 2004, was one of the most sophisticated physics experiments ever conceived. It used 4 of the most perfectly spherical gyroscopes ever created by humanity, orbiting 400 miles above the Earth, to measure this minuscule effect. After a year of painstaking observation and years of data analysis, the National Aeronautics and Space Administration confirmed that our planet's rotation does indeed drag space-time by about 0.000011 degrees per year. That may sound like an infinitesimally small number, but it matches Einstein's equations with extraordinary precision. Even our gentle planet, spinning just once every 24 hours, is capable of bending the very flow of time. Now, imagine a rotation billions of times faster and a gravitational field billions of times stronger. That is what happens near a neutron star. When a star much more massive than our Sun dies, it collapses under its own immense gravity, squeezing matter so tightly that protons and electrons are forced to merge into neutrons. The result is an object only about 12 miles wide but with a mass greater than that of our entire Sunday. To conserve angular momentum from its parent star, these tiny, dense objects spin unimaginably fast, up to 700 times per second. Astronomers call them pulsars because their powerful magnetic poles emit beams of radiation that sweep across space like cosmic lighthouses. As they rotate, they create the strongest known magnetic fields in the universe and twist space-time so violently that even light struggles to travel in a straight line near them. The National Aeronautics and Space Administration's NICA instrument, located aboard the International Space Station, has mapped these distortions around pulsars, showing that time near a pulsar ticks demonstrably more slowly than it does here on Earth. Einstein's equations tell us that this is not magic. It is a phenomenon called gravitational time dilation. Time, he showed, runs more slowly in regions of stronger gravity or for objects moving at faster speeds. When you are close to a massive spinning body, space-time itself is literally pulled into its rotation. You are dragged along, as if the very fabric of space is rotating you. This phenomenon reaches its most extreme and mind-bending conclusion near a Kerr black hole that is a black hole that spins. Named after the brilliant mathematician Roy Kerr, who first solved Einstein's equations for a rotating black hole in 1963, a Kerr black hole is perhaps the most exotic and strange structure that we know to exist in the universe. Unlike a simple, non-rotating black hole, which merely pulls everything inward towards its singularity, a Kerr black hole spins space-time itself around its axis. Close enough to its event horizon, the point of no return, the speed of that space-time rotation approaches the speed of light. At this point, nothing, not even time, can resist being dragged along. The region outside the event horizon where this inescapable frame dragging occurs is called the ergosphere. Within the ergosphere, nothing can remain stationary relative to a distant observer in space. Every particle, every photon of light, must rotate with the black hole. It is as if space itself becomes a viscous liquid, spinning in a vast, invisible, and unstoppable whirlpool. In the year 2021, using the National Aeronautics and Space Administration's Chandra X-ray Observatory, scientists observed matter spiraling around the supermassive black hole at the center of the galaxy, M87. They confirmed that it rotates at a speed near the absolute limit predicted by the theory of relativity. Inside that cosmic whirlpool, time behaves in ways that defy our intuition. If you could somehow hover safely near the ergosphere, an impossible feat for now, your clock would tick significantly slower than clocks back on Earth. For every single minute you experienced, hours, days, or even years could pass for the rest of the universe. Einstein called this the warping of time, a direct and unavoidable consequence of motion and gravity acting together. As he once profoundly wrote, "Time and space are modes by which we think, not conditions in which we live." The European Space Agency's Event Horizon Telescope, a global network of radio telescopes working in concert, captured the first ever image of a black hole's shadow in 2019, and later, in 2022, it released the image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. The luminous, glowing ring we see in these images is not light coming from the black hole itself, but from superheated matter spiraling around it, light that has been bent, delayed, and distorted by the extreme curvature of space-time. Those glowing arcs are direct visual proof that rotation and gravity, working together, can bend not just the path of light, but the very flow of time. The same laws, of course, apply on smaller, more familiar scales as well. Even the satellites orbiting high above the Earth experience these tiny but measurable time differences. The Global Positioning System, or GPS, that so many of us rely on every day, must constantly correct for both gravitational and velocity-induced time dilation. If left unadjusted, the atomic clocks on board GPS satellites would drift by about 38 microseconds per day relative to clocks on the ground. That tiny difference would be enough to cause navigation errors of several miles to accumulate every single day. So even here, in our relatively calm corner of the universe where space-time seems flat and time seems absolute, the bending of time is not just a strange theory. It is a practical part of our daily technological lives. When astrophysicists run computer simulations of the regions near a Kerr black hole, the mathematics becomes truly breathtaking. The equations show that extreme rotation can twist space-time so sharply that closed time-like curves can appear theoretical paths in space-time, where a particle could, in principle, loop back and arrive at an earlier point in its own timeline. Whether these time loops are physically real or just a mathematical artifact of the theory remains highly uncertain and is a record of this, subject of intense debate among physicists. But they emerge naturally and elegantly from Einstein's equations. In these extreme environments, the fixed, linear concepts of past and future lose their absolute meaning. The James Webb Space Telescope, with its incredible infrared precision, is now observing the accretion disks of distant quasars galaxies powered by supermassive, rapidly rotating black holes at their centers. The spectra of light from these disks, as measured by the JWST, show that the light has been stretched and redshifted, a clear sign that time is running slower in those intensely gravitational regions. Some of the light we detect from these objects today left those spinning giants over 13 billion years ago, meaning we are watching time itself being stretched across the vast expanse of the cosmos. Rotation, it turns out, does not just shape matter, it defines how time flows in its vicinity. The faster and denser the spin, the greater the warping of space-time. From our gentle, slowly turning planet to the violent, chaotic hearts of distant galaxies, the universe uses spin to sculpt both motion and time. What we call now is different everywhere, depending on how fast and how deep the local space-time is turning. Even light, which normally travels at the universe's ultimate and unbreakable speed limit, is forced to bend and slow down as it passes near rotating masses. The National Aeronautics and Space Administration's New Star and the European Space Agency's XMM Newton missions have captured X-ray echoes from around black holes. These are photons of light that have been trapped briefly in the rotating space-time before managing to escape. In these echoes, time stretches like a soft, elastic thread, measurable, predictable, yet endlessly strange. One might wonder then whether the universe itself is twisting time on the grandest scale of all. A large-scale cosmic rotation could, in theory, subtly influence the way time flows across billions of light-years. While current cosmological data from the European Space Agency's Planck satellite show no strong evidence for a universal spin, the question remains tantalizingly open. Even the faintest twist over cosmic distances might leave its fingerprints in the polarization of ancient light, subtle hints that time itself has a preferred, universal direction. As the renowned physicist Kip Thorne, a Nobel laureate and co-author of the science behind the movie Time's Interstellar Asterisk, explained, in the warped space-time near a spinning black hole, the future of one observer can literally become the past of another. Rotation does not just bend trajectories, it bends the very sequence of events, the fundamental rhythm of existence. And yet, for all its strangeness, this effect is consistent, predictable, and measurable. Time dilation around rotating bodies has been verified with incredible accuracy by atomic clocks aboard high-altitude aircraft, satellites in orbit, and in laboratories on mountaintops and at sea level. The faster you move, or the deeper you fall into a gravitational well, the slower your time flows relative to others. It is not an illusion, it is the universe keeping its books in perfect balance. So yes, rotation can and does bend time. But what is even more intriguing is why that bending seems to follow such a perfect, universal law. A law that links motion, gravity, and energy into one seamless continuum. From Einstein's elegant equations to every ticking satellite in orbit, it all points to one profound truth. The universe does not just move through time. It creates time through its motion. Take a slow, deep breath. Right now, your own personal sense of time is tied to the Earth's gentle spin, the sun's gravitational pull, and the galaxy's majestic turn. You are surrounded by a symphony of motion so precise that it literally writes the seconds you live in. And if rotation can bend time, what happens when time starts to control the spin? That is the mystery waiting in our next chapter. Every single second you live is shaped by motion, the ticking of your watch, the precise pulse of an atomic clock, even the steady, rhythmic beat of your own heart. All of these depend on something, somewhere. Spinning. Electrons rotate in their orbitals inside atoms. The Earth turns once every 24 hours, and as it spins, it drags space-time just enough to subtly change how time itself flows. At the equator, where the Earth's surface moves fastest, at about 1,037 miles per hour, clocks run just slightly slower than those at the poles. It is not because of temperature or air pressure, it is because of relativity. Einstein's groundbreaking theory showed that motion and gravity can stretch or compress the passage of time, depending on how fast you are moving and how deep you are within a gravitational field. So yes, in a very real and measurable way, spin controls time. But this leads to an even deeper question: who or what controls the spin? To begin to answer that, scientists look to the most reliable and precise keepers of time that humanity has ever built: atomic clocks. Inside these incredible devices, electrons whirl around the nuclei of atoms at fixed, quantized energy levels. When these electrons jump between those levels, They absorb or release photons of light at an exact, unwavering frequency. That frequency, as defined by the cesium-133 atom, is what sets the official length of 1 second, 9,192,631,770 cycles of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Those precise words, printed by the International Bureau of Weights and Measures, describe how every second of your life is calibrated to a tiny, invisible, atomic spin. The rotation of electrons inside atoms is a form of quantum spin, not a physical twirling like a spinning top, but a fundamental, intrinsic property of matter itself. In the world of quantum mechanics, particles carry specific spin values that determine how they behave in magnetic fields, how they form chemical bonds, and even how they obey the Pauli exclusion principle, the fundamental rule that dictates that no two electrons can occupy the same quantum state. So, at its very smallest and most fundamental scale, our modern timekeeping depends entirely on spin, not the grand turning of a planet, but the internal, quantum angular momentum of atoms themselves. But just as atomic spins govern time inside our laboratories, planetary spins govern time on a much larger, cosmic level. The Earth's rotation defines the length of our day, while its orbit around the Sun defines the length of our year. Yet, these motions are not perfectly fixed. They slowly drift and change over eons. As we have learned, the tidal forces from our moon are gradually slowing the Earth's spin, adding about 1.7 milliseconds per century to the length of each day. To keep our highly precise atomic time synchronized with our planet's slightly wobbly and slowing planetary time, scientists must use a system called leap seconds. Occasionally, the world's official atomic clocks are adjusted by 1 second to ensure they remain aligned with the planet's natural rotation. In a sense, we are constantly recalibrating our human-made time to match the Earth's ancient, cosmic spin. If you were to compare highly sensitive clocks at different latitudes on Earth, the differences in the passage of time would be measurable. A clock placed at sea level near the equator, where it is moving fastest due to the Earth's spin, runs slightly slower than a clock placed high in the mountains or near the poles. This is a beautiful, real-world demonstration of both special and general relativity at work. As the National Aeronautics and Space Administration explains, a clock on the equator ticks more slowly than one at the poles because it is both moving faster and is slightly deeper in the Earth's gravitational potential well. The difference is incredibly tiny, just a few nanoseconds per day. But it is real, and our technology must account for it. Your phone's GPS system, for example, must correct for this relativistic effect constantly. Each of the 24 operational GPS satellites orbits the Earth at about 8,700 miles per hour, 12,500 miles above the surface. In their high orbit, they experience weaker gravity and are moving at a higher speed relative to the ground, causing their onboard atomic clocks to run faster than clocks on Earth by about 38 microseconds every day. If this discrepancy were left uncorrected, it would cause navigation errors of several miles to accumulate every few hours, making the system useless. To keep our time consistent, engineers combine Einstein's elegant equations with real-world measurements, literally adjusting for the curvature of space-time caused by the Earth's mass and rotation. So, every time you check a map on your phone or receive a location signal, you are witnessing the profound truth of relativity in action, a quiet, constant collaboration between gravity, motion, and spin. But who started this cosmic spin in the first place? Astronomers trace it all the way back to the law of conservation of angular momentum, a fundamental and conserved quantity in physics. When our solar system formed about 4.6 billion years ago, a vast cloud of interstellar gas and dust began to collapse under its own gravity. As it shrank, any small, random initial rotation it had was amplified, causing it to spin faster and faster, just like a spinning ice skater pulling in her arms. That primordial motion distributed angular momentum to everything that formed within the resulting protoplanetary disk, the Sun, the planets, their moons, and all the asteroids. Each of these celestial bodies still carries a portion of that ancient, primordial rotation. There is no external force that continually keeps them spinning. They continue to spin because of inertia, the same law that dictates that an object in motion will stay in motion until something acts to resist it. In the near-perfect vacuum of space, where friction is almost entirely absent, these cosmic spins can persist for billions of years. So the most direct answer to the question, who controls the spin, is no one. Once set in motion by the fundamental laws of physics, the universe needs no guiding hand to keep turning. But the intricate relationship between spin and time grows stranger and more profound the deeper we look. Inside atoms, quantum spin determines energy states and chemical properties. On planetary scales, physical spin defines our days and shapes our climates. On cosmic scales, the spin of massive objects drags time itself along with it. And all of these different levels, from the quantum to the cosmic, are connected by one unbreakable law. Angular momentum is conserved. Time, in that sense, is not an independent entity flowing on its own. It is a reflection of how energy and spin interact with the fabric of space-time. In 2016, the European Space Agency's Gaia mission began to map the precise motions and positions of over 1 billion stars in our Milky Way galaxy. The resulting data revealed with stunning clarity that our entire galaxy rotates once every 230 million years, carrying our Sun and all its planets along in a vast, majestic spiral. Each star's orbit contributes to a grand cosmic timepiece, where one single rotation marks the passage of a galactic year, a rhythm of cosmic time. Just as atomic spin defines our seconds, stellar spin defines the eons. Even our own Sun spins, completing one rotation about every 27 days at its equator. But it does not spin as a solid body. Its poles rotate slower than its equator, a phenomenon called differential rotation. This twisting, shearing motion generates the Sun's powerful magnetic fields, which in turn shape solar flares and coronal mass ejections. When these magnetic storms reach Earth, they can distort our own magnetic field and even affect our satellites and power grids. So, from the atomic scale to the solar scale, spin is not a passive property. It actively sculpts magnetic fields, defines natural rhythms, and interacts with the very tools we use to measure the passage of time. Einstein's theory of relativity linked all of these seemingly disparate patterns together beautifully. In his field equations, the geometry of space-time is determined by the distribution of energy and momentum, and that includes angular momentum. In other words, spin curves time. If you could somehow remove all spin from the universe, space-time would become simpler, flatter, and far less dynamic. But when you add spin, it warps gently for planets and violently for black holes. We might then say that time itself is recorded in motion. The second is written in the language of atomic spin. The day is written in the language of planetary spin. The cosmic epoch is written in the language of galactic spin. Everything that moves measures time. And everything that measures time moves. In 2022, the James Webb Space Telescope observed distant galaxies whose light has traveled for over 13 billion years to reach us. Even in those primordial, infant galaxies, astronomers detected organized rotation, a clear sign that angular momentum existed almost immediately after the Big Bang. That means the fundamental law connecting spin and time has been in operation since the universe's very earliest seconds. Spin is not a product of time. It is part of what gives time its flow, its direction, its very meaning. So, if spin governs time, and spin itself arises naturally from the conservation of motion, then who or what controls it? The most precise and honest answer that science can currently offer is that the universe controls itself. Every spin is balanced by another. Every slowing motion is matched by a corresponding exchange of momentum elsewhere. Even the smallest quantum particle obeys these same unbreakable equations, ensuring that angular momentum remains perfectly conserved across all of space and all of time. The National Aeronautics and Space Administration's Jet Propulsion Laboratory put it simply: the laws of motion do not change. The universe runs on a perfect, self-correcting balance. What is lost in one place is gained in another. There is no master clockmaker, no hidden hand turning the gears. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its built-in, self-sustaining way of keeping everything aligned and in balance. From the atoms that make up your body to the stars in the sky above, the same fundamental principle governs every scale of existence. Even when systems decay, collide, or slow down, their angular momentum is not lost. It is transferred onward, keeping the great cosmic clock ticking. And so, when you ask who controls the spin, the universe gently answers, no one must. Motion is self-sustaining. It is the quiet, perfect balance that underlies both time and existence. Take a deep breath. The atoms within you are spinning in perfect harmony with the turning Earth, the orbiting moon, and the spiraling galaxy. You are already an integral part of that ancient motion. Every heartbeat is a tiny fraction of a universal rhythm that began long before clocks, calendars, or light itself. And as that rhythm continues, another question slowly rises. Not one of control, but of origin. One that stretches beyond motion into the very structure of the cosmos itself. If the universe depends on this perfect balance, what happened when that symmetry was first broken? That is where we drift next. If everything in the universe had once been perfectly balanced, perfectly symmetrical, nothing would ever have moved. There would be no stars, no atoms, no time, only a profound, eternal stillness, endless and unchanging. But the universe we know, the universe that is teeming with structure and life, began not with perfection, but with a tiny, crucial imperfection. It began with a small crack in the primordial symmetry that allowed everything we see today to unfold. In the language of physics, symmetry means that the laws of nature behave the same way in every direction, at every point in space, and for every observer. When symmetry holds perfectly, there is no reason for anything to change. But when that symmetry breaks, even slightly, motion appears, structure emerges from chaos, and time itself gains a direction, an arrow pointing from the past to the future. As the National Aeronautics and Space Administration's Goddard Space Flight Center describes it, the universe exists as we know it because perfect symmetry did not last. Let us drift back once more to those first, fiery fractions of a second after the Big Bang. According to the standard model of particle physics, the early universe was a hot, dense plasma where the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were once unified into a single, perfect superforce. But as the universe expanded and cooled with incredible rapidity, these forces began to separate, or freeze out, one by one. This process, known as spontaneous symmetry breaking, shaped everything from the fundamental structure of atoms to the very fabric of spacetime itself. The European Space Agency's Planck mission mapped the cosmic microwave background, the faint, ancient afterglow of the Big Bang, and found that it was astonishingly uniform across the entire sky. Yet, it was not perfect. Tiny variations in temperature, differences of only 1 part in 100,000, reveal the first signs of this broken symmetry. Those minute differences in energy density, born in the first moments of time, later acted as gravitational seeds, growing over billions of years into the vast cosmic web of galaxies, stars, and planets we see today. Without those tiny, initial fluctuations, the universe would have remained a smooth, static, and featureless mist, an endless and boring expanse of uniform energy. Even the existence of matter itself owes its origin to broken symmetry. When the universe was young and incredibly hot, energy was converted into matter and antimatter in nearly equal amounts. But the key word here is nearly. For every 1 billion particles of antimatter that were created, there were, for some reason, 1 billion and 1 particles of matter. That slight, almost insignificant imbalance, known as baryon asymmetry, meant that when all the matter and antimatter later annihilated each other in a burst of pure energy, a tiny fraction of matter survived. That leftover matter is what became the stars, the planets, and everything we can see and touch today. You are made of the survivors of a cosmic war. In the year 1964, the physicists James Cronin and Val Fitch discovered this subtle asymmetry in the behavior of subatomic particles, an effect now known as CP violation. Their groundbreaking experiment with particles called neutral kaons showed that the laws of physics do not treat matter and its antimatter mirror image with perfect equality. This discovery earned them the Nobel Prize in Physics and provided the first crucial clue that the universe has a built-in preference for one direction, one type of spin, one fundamental imbalance. As the Particle Physics Division at the European Space Agency notes, without this tiny violation of symmetry, the universe today would contain no matter at all, only a cold, dilute sea of light. So, in a very real sense, it was an imperfection that made everything possible. The precise mechanism behind this life-giving imbalance is still one of the biggest mysteries in physics and is being actively studied at places like CERN, the European Organization for Nuclear Research. At the Large Hadron Collider, scientists investigate particles like the Higgs boson, which plays a crucial role in breaking what is known as electroweak symmetry. When the universe cooled below a critical temperature, about 10 to the power of -12 seconds after the Big Bang, the Higgs field, which permeates all of space, gained a non-zero value. It is this field that gives fundamental particles their mass and breaks the once perfect symmetry between light and matter. It is often said that the Higgs field is what froze the universe into its current form, locking in the fundamental differences between particles that made all of chemistry and complexity possible. But not all symmetry breaking is violent or dramatic. Sometimes it is gentle and spontaneous, like the way a perfectly balanced pencil standing on its tip will eventually and inevitably fall in one random direction. The universe may have chosen a direction for time in a similar, spontaneous way. In the very earliest instance of time, it could have, in theory, flowed equally forward or backward. But a tiny, random fluctuation, perhaps in entropy, perhaps in quantum probability, pushed it forward, setting the irreversible arrow of time that governs our lives. As the physicist Sean Carroll once wrote, "The arrow of time is the result of a very low entropy state at the beginning of the universe, a state of broken symmetry that all later moments remember." So when we measure the passage of time, what we are really measuring is how far we have drifted from that initial state of perfect, timeless symmetry. Even the cosmic web, the vast, filamentary structure that connects clusters of galaxies across the universe, arises from this ancient imbalance. The James Webb Space Telescope's deep field images show galaxies forming along invisible threads of dark matter, and these threads trace the patterns of the earliest quantum fluctuations in density. Those fluctuations began as tiny, random variations in the primordial soup, which were then magnified to astronomical scales by the process of cosmic inflation, just moments after the Big Bang. What began as tiny, microscopic irregularities became the grand architecture of the entire universe. Without asymmetry, gravity itself could not work the way it does. A perfectly uniform distribution of matter would pull equally in all directions, resulting in no net force and therefore no motion. But with slight, almost imperceptible unevenness, gravity could begin to act, drawing matter into denser clumps, which formed the first stars and galaxies, and eventually, planets. The National Aeronautics and Space Administration's WMAP mission described it simply: if the early universe had been perfectly smooth, no structure could have formed. No galaxies, no stars, no life. Even at the deepest quantum level, fundamental particles betray this same fundamental imbalance. Neutrinos, for instance, are known to have a property called chirality. They all appear to spin in the same left-handed direction. This intrinsic handedness of the universe may be another profound echo of the original symmetry-breaking event. It is a pattern that repeats itself from the tiniest scales to the largest, from the spin of subatomic particles to the rotation of entire galaxies. Everywhere we look, the universe shows a subtle preference. Galaxies seem to rotate clockwise or counterclockwise in slightly unequal numbers. The molecules of life itself, like amino acids and sugars, also have a distinct handedness, a chemical bias called chirality that underlies all of biology. Though life arose on Earth billions of years after the Big Bang, its fundamental chemistry still reflects the same ancient asymmetry that was written into the fabric of the cosmos at its birth. This deep and mysterious connection between a cosmic imbalance and the structure of biology continues to fascinate scientists. A study from 2020 by the Astrobiology Institute at the National Aeronautics and Space Administration suggested that circularly polarized ultraviolet light from early, massive stars may have preferentially destroyed right-handed amino acids in interstellar space, leaving a surplus of left-handed ones to eventually seed life on Earth. If this theory is true, then even the fundamental molecular spin of life owes its direction to the universe's first broken symmetry. But perhaps the most elegant and profound demonstration of this principle lies hidden within the polarization of the cosmic microwave background radiation. The Planck satellite detected tiny, swirling patterns in this ancient light, a type of polarization known as B-modes, which may be the faint fingerprints of primordial gravitational waves. These waves would be the echoes of cosmic inflation, the universe's first and fastest period of expansion, and the very moment when perfect symmetry gave way to dynamic motion. If confirmed, they would be direct, observational evidence that the universe's very first act was to break a state of perfect balance. From the way light bends around massive objects, to the way galaxies align in the cosmic web, everything we can measure points back to that single, powerful principle. Imperfection drives creation. Symmetry is elegant, but it is also fragile and static. Break it, even just slightly, and the universe wakes up. As the theoretical physicist and Nobel laureate Murray Gell-Mann once said, "If the world were perfectly symmetrical, there would be nothing. It is the deviations, the slight differences in energy, in motion, in charge, that make reality as we know it possible." When we observe the deep universe through telescopes like the James Webb, what we are really seeing is the fossil record of broken symmetry, the first faint flicker of an imbalance that became time, structure, and light. And from that faint, primordial imperfection, everything else followed: galaxies, planets, oceans, and the quiet, gently rotating world beneath your feet. Take a slow, deep breath. You are living, breathing proof of asymmetry. You are being made from matter that once outnumbered its mirror twin by just 1 part in a billion. Every single atom in your body carries the indelible trace of that ancient cosmic bias, a preference preserved since the first microseconds of existence. So yes, the universe began because symmetry broke. Perfection gave way to motion, and motion gave rise to time. A small, almost insignificant crack in the cosmic balance created everything that would ever spin, shine, or breathe. And as we follow that first imbalance outward, we reach a new and profound puzzle. A question not about beginnings, but about what keeps the cosmos together despite its restless, eternal motion. Because if galaxies are spinning faster than they should be, something vast and invisible must be holding them in place. And from that new imbalance, a new mystery begins to turn, one hidden in the vast, silent darkness between the galaxies. Galaxies spin at what should be impossible speeds, The stars on their outer edges are moving so fast that, by all the known laws of physics, they should fly off into the intergalactic void, scattered like sparks from a rapidly turning wheel. And yet, they do not. Something unseen, something mysterious, is holding them in place. A silent, invisible mass that outweighs everything we can see by a factor of 5 to 1. Astronomers call this mysterious substance dark matter. It does not shine, it does not reflect, and it does not absorb light. It does not collide, melt, or form atoms. But it does have gravity. It pulls. And that immense, invisible pull is what keeps entire galaxies from tearing themselves apart. This profound mystery began in the 1930s, when the brilliant and eccentric Swiss astrophysicist Fritz Zwicky was studying the Coma Cluster, a vast collection of more than 1,000 galaxies, drifting some 320 million light-years away from us. Zwicky measured how fast the individual galaxies within the cluster were moving, and found that their visible mass, all the stars, gas, and dust he could account for, was not nearly enough to provide the gravitational glue needed to hold the cluster together. According to his calculations, the cluster should have flung itself apart billions of years ago. To solve this puzzle, he proposed something shocking and revolutionary for his time. An unseen form of mass must be present, providing the missing gravity. He called it dunkel materia, or dark matter. For decades, his groundbreaking idea remained a whisper on the fringes of astronomy, largely ignored by the EXO's scientific community. That is, until the 1970s, when the American astronomer Vera Rubin began meticulously measuring the rotation curves of spiral galaxies using data from the Kitt Peak National Observatory in Arizona. Rubin discovered something that defied all expectations based on Newtonian physics. She found that stars far from the galactic centers were orbiting just as fast as those much closer to the core. This was a stunning discovery. According to the laws of gravity, orbital speeds should decrease as you move further outward from the central mass, just as the outer planets in our solar system, like Neptune, move much more slowly than the inner planets, like Mercury. But Rubin's graphs were inexplicably flat. Every star, from the center to the very edge of the visible disk, moved at nearly the same constant speed. The only way to explain this was if the galaxies were embedded in a vast, invisible halo of matter that extended far beyond the visible stars, supplying the extra gravity needed to keep everything in orbit. As the National Aeronautics and Space Administration later summarized, the rotation curves of galaxies tell us in no uncertain terms that there is much more mass present than meets the eye. That unseen mass, dark matter, now appears to make up about 85% of all the matter in the universe. That is roughly 5 times more than all the visible, or baryonic, matter that makes up the stars, planets, and people. Scientists now estimate that every galaxy, including our own Milky Way, sits inside one of these vast dark matter halos, an invisible sphere of mass that can extend for hundreds of thousands of light-years beyond the galaxy's visible edges. Each of these halos acts as a cosmic scaffolding, binding the stars and gas together through its immense gravitational pull. Without it, beautiful spiral galaxies like the Milky Way would unravel and disperse in just a few 100 million years. Sophisticated computer simulations from the National Aeronautics and Space Administration's Goddard Space Flight Center have shown that dark matter provides the essential cosmic glue that allowed galaxies to form in the first place, and that allows them to merge and persist over cosmic timescales. The European Space Agency has also observed this invisible structure for decades through a phenomenon known as gravitational lensing, which is the bending of light by massive objects as predicted by Einstein's theory of general relativity. When light from extremely distant galaxies passes near a massive galaxy cluster that is filled with dark matter, the unseen mass warps the fabric of space-time, magnifying and distorting the background light into beautiful, graceful arcs and rings. The European Space Agency's Euclid mission, which was launched in 2023, is specifically designed to map this subtle lensing effect across billions of galaxies, with the goal of creating the most detailed, three-dimensional chart of the universe's dark matter distribution ever made. Even before Euclid, the Hubble Space Telescope gave us stunning glimpses of this cosmic lensing effect. In 2006, Hubble captured a remarkable image of the Bullet Cluster, a system where two galaxy clusters had collided with each other. X-ray images from the National Aeronautics and Space Administration's Chandra Observatory showed that the hot gas, which is ordinary matter, had slowed down and lagged behind after the collision. But when scientists mapped the total mass of the system using gravitational lensing, they found that the bulk of the mass lay far ahead of the gas, having passed right through the collision without interacting. It was clear, direct proof that most of the mass in the cluster was invisible and non-interacting, an independent, unseen component of the universe. Dark matter does not interact with light or any other form of electromagnetic radiation, which is why it cannot be seen directly. It seems to interact only through the force of gravity, and possibly through the weak nuclear force. The leading theoretical candidates for what dark matter could be are hypothetical particles such as WIMPs, which stands for weakly interacting massive particles, or another type of particle called axions. Both of these are predicted by extensions of the standard model of particle physics. Enormous and incredibly sensitive experiments, like the XENONNT experiment deep underground in Italy and the Lux-Zeppelin experiment in a former gold mine in South Dakota, are currently trying to detect these elusive particles by searching for the rare, faint flashes of light that would be produced if one happened to collide with an atomic nucleus in their detectors. So far, no confirmed detection has been made, but the silent, patient search continues, shielded deep underground from the constant shower of cosmic rays. Meanwhile, the National Aeronautics and Space Administration's Fermi Gamma-ray Space Telescope has been searching the sky for subtle signatures of dark matter particles annihilating each other in the dense centers of galaxies. And the James Webb Space Telescope has begun observing the faint structures of the very first galaxies in the early universe, which formed less than 400 million years after the Big Bang. Even at that incredibly young age, these infant galaxies already showed signs of stable rotation, suggesting that their dark matter halos were already in place, providing the gravitational framework for them to form. As scientists from the European Space Agency wrote, dark matter must have formed very early, shaping the large-scale structure of the universe, long before the first stars ever ignited. On cosmic scales, dark matter determines not only how galaxies spin, but how the entire universe evolves. Large-scale computer simulations, like the National Aeronautics and Space Administration's Illustris and the International Eagle projects, show that without the gravitational influence of dark matter, galaxies as we know them would never have formed at all. Ordinary matter would have remained too evenly spread out, unable to clump together under its own relatively weak gravity. Dark matter provided the invisible scaffolding, the gravitational wells into which ordinary matter could fall and condense. It is, as the astrophysicist Neil deGrasse Tyson has poetically put it, the greatest cosmic mystery of our time, a shadow universe holding our own in its invisible grip. Though it is invisible, dark matter leaves its gravitational trail everywhere. It shapes the distribution of galaxy clusters. It influences the formation of the cosmic filaments that connect them, and it even affects the overall expansion rate of the universe. Dark matter does not emit any radiation, but its collective gravity acts as a brake, slowing down the outward expansion that began with the Big Bang. This cosmic tug-of-war between the inward pull of dark matter's gravity and the outward push of dark energy's mysterious acceleration is what defines the large-scale structure and ultimate fate of everything. So, just how fast are galaxies really spinning? Let's take our own Milky Way as an example. Our Sun orbits the galactic center at a speed of about 514,000 miles per hour, completing one full rotation every 230 million years. At that incredible speed, and given the amount of visible mass we can account for, our galaxy should have torn itself apart billions of years ago. But the vast dark matter halo surrounding it, which extends perhaps 200,000 light-years beyond the visible disk, adds the necessary gravitational mass to keep it whole and stable. This delicate balance between a galaxy's spin and the gravity of its dark matter halo is crucial. If dark matter were just slightly less abundant, galaxies would scatter their stars into the void. If it were slightly more abundant, they would have collapsed under their own weight long ago. The European Space Agency's Planck satellite has provided our most precise estimates of the universe's composition: about 68% dark energy, 27% dark matter, and only 5% ordinary matter. That means that everything we can see, every star, every planet, and every person, accounts for just 1/20th of what actually exists in the universe. What makes dark matter so deeply puzzling is that it does not fit neatly into our current understanding of physics. We can measure its gravitational pull, we can map its distribution across the cosmos, and we can simulate its effects with incredible accuracy, but we cannot yet identify what it is made of. Some physicists have even suggested that our understanding of gravity itself might be incomplete and in need of revision. Modified theories of gravity, such as modified Newtonian dynamics, and TV's tensor vector scalar gravity, attempt to explain the observed rotation of galaxies without invoking the existence of dark matter. But so far, the dark matter hypothesis remains the simpler and more consistent explanation for a wide range of cosmological observations. New missions are poised to finally solve this profound enigma. The European Space Agency's Euclid and the National Aeronautics and Space Administration's Nancy Grace Roman Space Telescope will work together to map billions of galaxies and measure how dark matter has shaped their growth and evolution over 13 billion years of cosmic history. Their ultimate goal is not only to understand the nature of dark matter, but also to reveal how it interacts, or does not interact, with dark energy, the even more mysterious force that is driving the universe's accelerating expansion. Even the James Webb Space Telescope is contributing to this quest. By observing the earliest galaxies, the JWST allows scientists to test whether dark matter behaved in the same way across all of cosmic time. If the formation of those ancient systems matches our current models, it will strengthen the case that dark matter's invisible hand has always been at work, shaping the cosmos from the very beginning. It is a strange and humbling thought that what keeps the galaxies whole is something we cannot see or touch. Yet, its silent, gravitational melody is what holds the entire cosmos in tune. Without it, the universe would lose its shape, its stars would be flung into darkness, and its great clusters would be unbound. Dark matter is the quiet architecture of existence, a vast, invisible framework made not of light, but of stability. Take a deep breath. Every star you have ever seen, every distant galaxy that has drifted across the lens of your telescope, is balanced upon something invisible. You are living in a universe held together by shadows, by unseen forces that act without ever being seen, guiding the motion of everything that spins. And as we trace that invisible hand through the cosmic darkness, we begin to notice something even stranger. If dark matter holds entire galaxies together, could it also have shaped the very direction of life itself, even down to the fundamental spin of molecules? Perhaps the same hidden force that binds the galaxies has also left its subtle fingerprint within the delicate spirals of life, a trace we are only just beginning to uncover. Every single living thing on Earth is twisted, just slightly. Your DNA, the very blueprint of your existence, spirals to the right. The amino acids that build every single cell in your body invariably bend to the left. This fundamental one-sidedness, a property known as chirality, is one of the deepest and most profound mysteries in all of biology. It means that life, down to its smallest and most fundamental molecular shape, has a preferred direction, a built-in bias, a spin. In the world of chemistry, chirality simply means handedness. Just like your left and right hands are mirror images of each other that cannot be perfectly superimposed, certain molecules can exist in two distinct forms, one left-handed and one right-handed. In most non-biological chemical reactions, both of these versions, or enantiomers, are produced in equal amounts. But in the chemistry of living organisms, only one hand is ever chosen. DNA and RNA, the molecules that carry our genetic information, always twist into a right-handed helix. Amino acids, the building blocks of proteins, are always found in their left-handed form. It is as if, long, long ago, at the dawn of life, a permanent decision was made, and all of life has followed that particular spin ever since. For decades, scientists have puzzled over why this should be. If the laws of chemistry alone can produce both directions equally, then something outside of biology, some external influence, must have nudged early life toward one side over the other. One of the most compelling clues comes from the light of ancient stars. Light waves can be polarized, meaning they oscillate more strongly in one particular direction. In the early universe, young, massive stars emitted intense ultraviolet radiation that could become circularly polarized as it passed through and scattered off magnetically aligned dust clouds in interstellar space. According to studies conducted by the National Aeronautics and Space Administration's Astrobiology Institute and Ames Research Center, this circularly polarized light could have selectively destroyed one-handedness of amino acid molecules more than the other. Over millions of years, in the vast molecular clouds where solar systems are born, this subtle preference could have created a small but significant surplus of one type of molecule, seeding the ultimate handedness of life itself. The European Space Agency's Rosetta mission provided intriguing evidence to support this theory. When Rosetta's Philae lander touched down on the surface of Comet 67P, Churyumov-Gerasimenko, in 2014, its instruments detected a variety of complex organic molecules, including the chemical precursors to amino acids. Subsequent analysis of their structure showed signs of asymmetry, hinting that a chiral bias may have already existed in the primordial material of our solar system, long before life ever began on Earth. This implies that the fundamental direction of life's molecules could have been inherited from interstellar chemistry, a preference shaped by cosmic light and motion long before our planet even formed. Another powerful clue comes from meteorites. In the year 1969, the famous Murchison meteorite fell in Australia. This ancient rock from space was found to contain more than 70 different types of amino acids. And when scientists later analyzed them with incredible precision, they discovered a slight but consistent excess of the left-handed forms. As the National Aeronautics and Space Administration's Johnson Space Center explained, the Murchison meteorite preserves the chemical fingerprints of the molecular cloud from which our solar system formed. Those ancient fingerprints show that the early solar system already had a preferred molecular direction, a bias that life on Earth would later adopt and amplify. But why left-handed for amino acids and right-handed for DNA? It might be more than just a cosmic coincidence. Some researchers believe that these opposite orientations actually complement each other perfectly. One direction determines the structure, while the other ensures stability. Left-handed amino acids can fold into complex protein structures that can then bond perfectly and efficiently with right-handed nucleic acids like DNA, forming the precise biochemical harmony that sustains all of life. If you were to reverse that orientation, the chemistry simply would not work as well. Still, this profound asymmetry did not emerge randomly from nothing. It may trace its origins all the way back to the earliest quantum imbalances, the tiny fluctuations in energy and spin that occurred within microseconds after the Big Bang. Experiments at major particle physics laboratories like CERN and Fermilab have confirmed that some subatomic particles, such as neutrinos, always spin in a left-handed direction relative to their motion. This universal handedness, a phenomenon known as parity violation, shows that even the most fundamental laws of physics are not perfectly symmetrical. In the year 1956, the brilliant physicists Chien-Shiung Wu and Tsung-Dao Lee proved this through their historic beta decay experiment. They showed that the weak nuclear force, one of the four fundamental forces of nature, does not treat left and right equally. As Wu herself later described it, nature is not as symmetrical as it appears. If even the universe's basic forces favor one type of spin over another, then it is not such a great leap to imagine that life's molecules, which are governed by those same forces, also inherited this deep cosmic preference. On Earth, this pattern of asymmetry continues everywhere we look, from the swirling arms of hurricanes to the spiraling growth of seashells and the climbing patterns of vines. Spin and asymmetry are built into the very design of nature. The Coriolis effect, caused by the Earth's rotation, determines the direction of large-scale storms counterclockwise in the northern hemisphere and clockwise in the southern. Even our planet's magnetic field has a defined polarity, which flips occasionally over geological time but never loses its fundamental sense of direction. The farther we look out into space, the more this cosmic bias seems to reappear. In 2011, the astronomer Lior Shamir analyzed tens of thousands of spiral galaxies using data from the Sloan Digital Sky Survey. He found a small but statistically significant difference in the number of galaxies rotating clockwise versus counterclockwise. That cosmic scale imbalance suggested the presence of a large-scale directional pattern in the universe, perhaps a faint relic of the universe's overall spin in its earliest moments. If this is true, then the same fundamental asymmetry that governs the rotation of entire galaxies may echo all the way down to the molecular structures of life. This profound connection between cosmic motion and biochemistry has fascinated scientists for decades. A study from 2021 by the Tokyo Institute of Technology used computer simulations to model the effects of circularly polarized light on amino acids in a realistic interstellar environment. They found that even a very small imbalance in the spin of the photons could lead to a measurable and significant difference in the resulting molecular chirality. In other words, light, shaped by the rotation of the cosmos, might have literally set the direction for life to follow. It is easy to forget that light itself carries a form of spin. Photons can have either right-handed or left-handed circular polarization, a kind of intrinsic angular momentum that affects how they interact with matter. When the light from early stars passed through interstellar magnetic fields that were twisted by galactic rotation, that spin could have been imprinted as a bias onto the very molecules it touched. Even the simplest dust grains floating in the vast, cold spaces between stars might have been aligned and polarized by the galaxy's overall motion, causing them to scatter light in a way that favored the creation or survival of one molecular hand over the other. The James Webb Space Telescope is now studying these complex organic molecules in nearby star-forming regions like the Taurus Molecular Cloud and the Orion Nebula. The JWST's sensitive infrared instruments have detected a host of prebiotic compounds, including long carbon chains and nitriles, forming under the direct influence of polarized starlight. These groundbreaking observations suggest that the chemical seeds of life naturally inherit a sense of directionality from their cosmic environment. So when we ask whether the universe's spin decided the direction of life, the accumulating evidence points to a quiet, yet compelling yes. From the preferred spin of entire galaxies to the intrinsic handedness of neutrinos, from the polarization of starlight to the chirality of life's molecules, every scale of nature seems to possess a subtle preference for motion in one direction over another. It is as if life is not a random accident at all, but a beautiful and intricate continuation of the universe's earliest rotation, a preference written into every single strand of your DNA. As the great astrophysicist and science communicator Carl Sagan once said, "We are made of star stuff. Perhaps we are also made of the spin of those stars, the angular memory of their ancient light." Take a quiet, deep breath. Every cell inside your body still carries that fundamental twist, a microscopic, living echo of the universe's majestic turning. From the grand dance of the galaxies to the delicate spiral of your own DNA, the same primordial motion continues, smooth and silent, across billions of years. And now, as we look deeper into that profound cosmic connection, another, more somber question emerges, not about beginnings, but about endings. If everything that spins must one day slow down, what happens when the universe itself forgets how to turn? That is the mystery that is waiting quietly ahead. Every rotation eventually slows. The Earth's days are gradually, imperceptibly, getting longer. Distant galaxies are drifting apart, their graceful, tightly wound spirals losing momentum as the universe expands. Even the stars themselves, those brilliant furnaces of motion and nuclear fusion, are burning down their fuel, one by one. The universe that began with a great, primordial spin seems to be slowly, inexorably, unwinding. But can motion truly vanish forever? Or does it simply fade, spreading thinner and thinner across the expanding fabric of space and time? The National Aeronautics and Space Administration physicist Michel Thaler once said, "Energy doesn't disappear, it just disperses." So too, it seems, with spin. It does not simply stop, it diffuses. Our own planet, for instance, is already losing its youthful rhythm. Each and every century, the Moon's persistent gravitational pull slows the Earth's rotation by about 1.7 milliseconds. This energy is not lost. It is transferred outward to the Moon's orbit. The result is that the Moon is slowly drifting away from us by nearly 1.5 inches every single year. This is a gentle, cosmic dance that has been playing out for billions of years. Laser reflectors left on the lunar surface by the Apollo astronauts have allowed scientists to confirm this drift with millimeter precision. If this process continues unabated, the Earth's rotation will one day lock with the Moon's orbit, and our planet will always show the same face to the Moon, just as the Moon already does to us. It will mark the end of the powerful ocean tides as we know them, the end of the daily cycle of ocean currents and atmospheric circulation. Our planet's vibrant spin, once the engine of life, will have faded into a state of quiet equilibrium. Elsewhere in our solar system, the same story of slowing rotation is playing out. Mercury is already trapped in a 3-to-2 spin-orbit resonance, meaning it rotates exactly 3 times for every 2 orbits it completes around the Sunday. Venus, with its incredibly dense atmosphere creating tidal friction, has slowed to an almost unearthly crawl, with one full rotation taking 243 Earth days, and it spins in the opposite direction of its orbit. Even Mars, whose day is only slightly longer than ours, is gradually losing its rotational speed. Over vast cosmic timescales, it becomes clear that spin is not a permanent feature. It is a finite rhythm, a cosmic clock winding down. This slowing process continues beyond individual planets and into the very heart of distant galaxies. Using powerful instruments like the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope, astronomers have measured the rotation rates of spiral galaxies that are billions of light-years away. When they compare these ancient galaxies with modern ones closer to us, they find that the ancient systems appear to have spun faster, with tighter spiral arms, denser cores, and more concentrated angular momentum. As cosmic time passes, a combination of gravitational interactions with other galaxies and the overall expansion of the universe gradually saps that primordial motion. According to a study from 2020 from the Leibniz Institute for Astrophysics in Potsdam, Germany, galaxies can lose a significant portion of their spin through collisions and mergers. When 2 galaxies merge, their individual stars rarely collide directly, but their vast, invisible dark matter halos interact powerfully, redistributing angular momentum outward into the resulting larger halo. This process tends to leave the merged galaxy rounder, slower, and more diffuse. The graceful, dynamic spiral gives way to the more static, settled form of an elliptical galaxy. The European Space Agency's Gaia mission has mapped the precise motions of over 1.8 billion stars in our own Milky Way, revealing that even our home galaxy is slowly evolving towards a state of greater stillness. Its outer arms, once more tightly wound, are gradually stretching and becoming less defined. Over the next few billion years, gravitational friction with its own dark matter halo and with nearby satellite galaxies will continue to drain its spin, softening its beautiful spiral form. Eventually, in about 4.5 billion years, the Milky Way and our nearest large neighbor, the Andromeda Galaxy, will collide not in a chaotic crash, but in a slow, silent fusion that will take hundreds of millions of years. Their combined rotation will eventually settle into a single, massive, and nearly motionless elliptical galaxy. But spin does not simply vanish when the stars fade, it transforms. When a very massive star reaches the end of its life, it collapses inward under its own gravity. In this collapse, it conserves its angular momentum, causing it to spin faster and faster, creating some of the most extreme objects in the universe. This process creates neutron stars, city-sized objects that can rotate hundreds of times every single second. The National Aeronautics and Space Administration's NISA instrument on the International Space Station has observed pulsars spinning at an astonishing 716 times per second. Their powerful beams of radiation sweeping through space with the precision of the best atomic clocks. Yet, even these incredible cosmic lighthouses eventually slow down, radiating away their rotational energy in the form of powerful magnetic fields and, more subtly, as gravitational waves. As time expands even further into the deep future, rotation will become an increasingly scarce commodity. The stars will fade and die, and black holes, the last great engines of spin in the universe, will themselves slowly evaporate through a process known as Hawking radiation. In the year 1974, the brilliant physicist Stephen Hawking predicted that even black holes are not eternal. They slowly leak energy back into the universe and, in doing so, lose their mass and their angular momentum over unimaginable timescales. A spinning black hole, known as a Kerr black hole, will gradually transfer its rotation to the surrounding space-time, creating faint, outgoing ripples of energy that will stretch and fade as they travel across the ever-expanding universe. The Future Laser Interferometer Space Antenna, or LISA, mission, which is planned for the 2030s, will be designed to detect these gravitational whispers, the faint waves caused by spinning black holes merging and eventually fading away. Each detection will be a direct record of rotational energy being released back into the fabric of space-time, a final echo of motion across billions of light-years. Even long after the black holes themselves are gone, their rotational memory will remain, imprinted forever in the subtle geometry of the universe. So, will the universe ever truly and completely stop spinning? The answer is probably not. According to the fundamental laws of physics, angular momentum cannot be created or destroyed, only transferred from one system to another or spread thinner across an ever-expanding sea of particles. As the National Aeronautics and Space Administration explains, in a closed, isolated system, total angular momentum is always conserved. The universe as a whole, in this sense, never stops moving. It only redistributes its motion into ever more dilute forms. Still, there may come a distant age when motion becomes practically imperceptible. In the very far future, long after the last stars have died and the galaxies have faded into darkness, the universe will enter what physicists call the heat death. Energy will be evenly and thinly distributed everywhere. There will be no temperature gradients, no flow of energy, no reason for anything to move in an organized way. Rotation will still exist mathematically, but without contrast, without structure, it will have no physical meaning. Some cosmologists, including Lawrence Krauss and Brian Greene, describe this ultimate future as the cosmic silence, the final, absolute calm after every vibration, every orbit, and every last spin has faded away. In that impossibly distant epoch, protons themselves may have passed, decayed, and the last black holes may have faded into final bursts of faint radiation. Only a cold, dilute gas of background photons and neutrinos will drift endlessly and aimlessly through a vast, dark space, carrying the last, faint traces of the universe's once grand rotation. The James Webb Space Telescope peers deep into the universe's past, but in doing so, it also reminds us of the universe's ultimate future. Every ancient, fast-spinning galaxy it observes is another tick backward on the great cosmic clock, showing us how vibrant rotation once defined the universe's structure. In its breathtaking images, we see both the fire of beginnings and the embers of endings, motion kindled by a broken symmetry, and motion destined to fade into an eternal stillness. Even so, spin leaves indelible fingerprints that cannot be fully erased. From the faint polarization patterns in the cosmic microwave background to the subtle curvature of space-time around dying stars, the memory of motion will remain encoded in the universe's fundamental design. It is not the movement itself that we will lose, only the strength to notice it. Right now, the Earth's molten core still turns beneath you. The stars still follow their majestic orbits, and the Milky Way still drifts silently through the cosmic darkness. Every motion you know, every rhythm you feel, is a precious flicker of that ancient, primordial rotation, one that will outlast you, but not eternity. And when that eternity finally arrives, when the last cosmic spin finally stretches into an unbreakable silence, something else will still remain. Not the movement itself, but the memory of that movement. Because even when the universe forgets how to turn, its very geometry will still remember that it once did. As we approach that distant horizon of ultimate stillness, another, more personal question quietly unfolds. If every atom, every planet, and every galaxy is slowly, inevitably, slowing down, what does that make us? The ones who are still moving, still thinking, still feeling, within it. That is where our final story begins. With a form of motion not of the cosmos, but of consciousness itself. Every single atom inside your body is spinning. The electrons orbiting their nuclei, the protons and neutrons bound together within those nuclei, and the quarks deep inside them all are caught in a state of ceaseless, fundamental motion. That motion is not random. It is a continuation. It is the faint, unbroken echo of the universe's very first rotation, a memory carried forward for 13.8 billion years. When you move, when you breathe, when your heart beats, you are not performing actions that are separate from the cosmos. You are participating in its oldest and most fundamental memory, motion itself. In the world of physics, the law of conservation of angular momentum is what describes the persistence of spin, the unbreakable rule that keeps motion alive across the eons. It is the reason why galaxies still turn, why planets still orbit their stars, and why atoms still vibrate with energy after nearly 14 billion years of cosmic history. According to the National Aeronautics and Space Administration's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared between different systems. This profound law means that every single spin in the universe, from the grandest galactic rotation to the smallest quantum vibration, is a direct continuation of the same original rotational energy that began at the moment of the Big Bang. In the very beginning, the universe was not still. As we have seen, precise measurements from the European Space Agency's Planck satellite show that the cosmic microwave background, the faint, ancient afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in its temperature. Some cosmologists interpret these patterns as the fossilized traces of the universe's first angular momentum, the original, primordial twist that set everything into motion. That primordial spin never vanished. It simply fragmented, spreading itself across all scales, from superclusters of galaxies down to the atoms that make up you and me. When stars form, vast clouds of hydrogen and helium gas collapse under their own gravity. As these clouds shrink, they inevitably rotate faster and faster, conserving their initial angular momentum, just like an ice skater pulling in her arms to accelerate her spin. This same fundamental rule gives rise to the swirling accretion disks we see around young stars, the flattened planes of planetary systems, and even the chaotic maelstroms of matter spiraling into black holes. Each planet, each moon in our solar system carries a small fragment of that original nebula spin, embedded forever in its orbit and its own rotation. And within those planets, inside every rock, every ocean, and every living cell, the same pattern of inherited motion continues at ever smaller and more intricate scales. The electrons that define all of chemistry and all of life obey the quantum property of spin, a fundamental, intrinsic, angular momentum that is a property of all elementary particles. This spin, as we have learned, is not a literal spinning like a tiny ball, but a more abstract quantum state, a numerical value that determines how particles interact with magnetic fields and with each other. Without the property of quantum spin, the rules of chemistry would not exist. Atoms could not bond together to form molecules, and the stable, complex structures of life would be impossible. The National Aeronautics and Space Administration's Quantum Laboratory Initiative describes particle spin as the fundamental engine of atomic structure, the essential difference between a universe of inert, chaotic particles and a universe of stable, structured matter. In this very deep and physical sense, you could say that every piece of matter in the universe carries with it an ancient choreography. The quantum spin of particles leads to the existence of magnetic fields, which in turn lead to the formation of complex structures, which leads to the birth of stars and planets, and ultimately to the emergence of life. Your own neurons fire using electrical potentials that are shaped by these same fundamental electromagnetic principles. Every single thought that crosses your mind is, at its core, a complex and beautifully ordered alignment of charged particles, a form of organized motion. So when we ask whether consciousness might be the universe remembering its own motion, the question is not merely poetic, it is deeply physical. Each of your brain waves, each neural signal, is built upon the foundation of tiny rotations that have existed since the dawn of time. The faint magnetic fields generated by the activity in your brain are faint echoes of the same electromagnetic principles that guide the colossal magnetic fields of pulsars and magnetars. As the astrophysicist Neil deGrasse Tyson has said, "We are not in the universe. We are part of the universe, and the universe is in us." From a purely scientific viewpoint, memory is a form of pattern preservation, a way of encoding information in physical states. Atoms can be said to remember through their spin orientation. Cells remember through the complex structure of their molecules. Stars remember their origins through their rotation curves. And the universe as a whole remembers its history through the very geometry of space-time itself. Einstein's theory of general relativity teaches us that the distribution of energy and momentum in the universe is what shapes the curvature of space-time. Therefore, every movement, every rotation that has ever occurred has left a small, permanent indentation, a tiny swirl in the overall geometry of reality. This is the phenomenon of frame dragging, which was confirmed with astonishing precision by the National Aeronautics and Space Administration's Gravity Probe B experiment in 2011. The probe measured how the Earth's relatively slow rotation subtly twists the fabric of space-time around it, like a spoon gently stirring honey. It was the first direct proof that spin is not a property that is confined to objects. It is a property that extends out into the very fabric of the cosmos. In a similar, albeit infinitesimally smaller way, even your own movements, your every gesture, also disturb the fabric of space-time, ever so slightly. The only difference is one of scale. The atoms in your body are spinning billions upon billions of times per second, generating tiny magnetic interactions that are measurable by highly sensitive quantum sensors. Each of these microscopic rotations contributes to the ongoing, unbroken record of motion that began long before humanity ever existed. If all motion leaves its indelible traces in the fabric of space-time, then perhaps what we call awareness, what we call consciousness, is simply the way the universe perceives those traces through us, not as a disembodied emotion or a spirit, but as a form of physical continuity, a state where matter becomes complex enough to recognize its own persistence through time. Consciousness, in this purely scientific and non-mystical sense, could be seen as a system's capacity to reflect and model its own internal state. And that reflection is written in the language of movement. Even light, the fundamental messenger of the cosmos, carries angular momentum. Photons possess a quantum spin value of 1, which determines how they can be polarized and how they interact with matter. The faint polarization patterns that we can still detect in the cosmic microwave background act as the oldest existing record of rotational memory in the entire universe. The European Space Agency's Planck satellite and the National Aeronautics and Space Administration's WMAP mission mapped these faint, ancient swirls in exquisite detail, showing faint B-mode patterns that are believed to be the signatures of primordial gravitational waves rippling out from the universe's very first, violent motion. So when you gaze up at the starlight on a clear night, you are literally seeing the memory of spin light that has been twisted, stretched, and polarized by billions of years of cosmic motion. And that ancient light enters your eyes, triggers a cascade of chemical reactions in your retina, and becomes a part of your own neural motion. In that beautiful, tangible way, the universe does not just remember its spin, it continues to experience it through every single observer it creates. Even as the cosmos expands, cools, and slows down, these traces of motion will persist. Galaxies may slow their rotation, but their total angular momentum never truly disappears. It is passed on to the diffuse intergalactic gas, to the vast dark matter halos, and to the radiation that streams out into the void. The James Webb Space Telescope has detected faint, ghostly filaments of gas stretching between ancient galaxies, vast cosmic structures that were shaped by these very transfers of spin. Every wisp of matter in the universe still moves to the ancient rhythm that was set 13.8 billion years ago. And when the very last stars have faded, and all motion has seemingly slowed to a complete silence, those patterns that have been encoded in gravitational waves, in the intrinsic spin of particles, and in the frozen light of the cosmic background, will still ripple faintly through the dark, empty space. They will not be gone. They will be written into the very shape of everything that remains. Like the fossilized imprints of ancient rotation, they will form the universe's deepest and most enduring kind of memory. Motion preserved as pure geometry. The great astronomer Carl Sagan once reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the language of modern physics, that act of knowing is not mystical. It is achieved through motion, through energy, and through spin. The universe is a system that continuously encodes and retrieves its own history through its physical evolution. Take a deep breath. Slowly, every atom inside you continues to turn with the same fundamental spin that once ignited the very first stars. You are a moving archive, a living, breathing part of the universe's ongoing memory. And as we follow that profound idea that motion may be the cosmos, remembering itself, a new and final horizon opens. Because if memory is movement, then perhaps what we call life is simply the brief, precious moment when the universe pauses, just long enough to notice that it is still spinning. If this quiet journey through the spinning cosmos has brought you even a small moment of peace or wonder, I am deeply grateful that you have spent it here with me. A gentle like on this video, or a soft tap on the subscribe button, means more than you can possibly imagine. It is what keeps me creating these cosmic lullabies for wandering minds like yours. And if you are kind enough, I would love for you to tell me in the comments where you are listening from tonight and what time it is in your corner of the world. I love seeing how far these quiet adventures drift across our spinning planet, from one sleepy corner to another. Your words, your presence, even your silent listening, they are like little stars guiding me forward, and I treasure them deeply. Until we meet again, may the universe turn softly around you,